Okay, so recently I got a question where I had to use Doppler effect, um, but the usual Doppler effect that is taught for sound waves, well, that doesn't work for light. So for light, you have to use relativistic Doppler effect. Now, why does this happen? That happens because, I mean, special relativity, of course, and the formula that we get is actually different from the usual formula. So here's a small derivation of the formula for a special case, basically. So this is the special case where O dash is moving with velocity v in the x direction as seen by O. And O is the source. It is emitting light of frequency f, wavelength lambda, and time period t as seen in its own frame. Right, and it records when the light waves will reach O dash, right? And right, it can do that. So O can do that, and then once you have the timing required for those two events, so the event is basically your photons. I'm gonna use photons here because I don't have any better word. I could use crests and whatnot, but then let's just use photons, right? So that will make it easier to understand. So what I'm picturing right now is that light is just a bunch of photons which are emitted from O, and those photons have wavelength lambda, so that distance between them, and they are emitted at an interval, the time interval of capital T, which is the time period, and 1 upon capital T is defined as the frequency. So that's the, yeah, that's the thing in our S reference frame, right? And you can also figure out what time interval will be required for two consecutive photons to hit our O dash observer as seen from O. So that we're calling T2 minus T1. So X1 T1 is, so these are the coordinates of event E1, which is a particular photon hitting O dash. And then E2 is the very next photon hitting O dash. So for that you have coordinates X2 T2, and these are in the reference frame of S. Then you want to use our Lorentz transform, which by the way I should explain first of all. So this is the Lorentz transform. Now you might be thinking, what is all of this that I've written down? You should watch a video of mine where actually I have all of this like in a slow scroll down kind of manner, so you can read everything. But right now I'll just explain what's going on. So I'm using this Lorentz. Where is that? Okay, so I'm using the Lorentz transform. So this is for the particular case when O and O dash are moving the same line, right? And with respect to O, your O dash is moving with velocity v along the x-axis, of course. And yeah, and your S reference frame, in that reference frame, your O is not moving. So O is an observer, O dash is an observer, right? And I should actually explain the whole concept itself, but then you should really watch that video where you actually, like, you can read everything what I've written down. And yes, I do accept that everything that I've written down is kind of not in a very good state because I didn't actually draw anything. There's no like pictures, and it's all very jumbled up manner. I'm using weird symbols. I know that, but you have to go through that pain. It's just a little bit of pain, and you will get to learn something new, right? Just go through that, and you will be able to understand what's going on over here. So this thing, this little thing, it's called the Lorentz transform. So it's basically used to figure out what will be the coordinates of a certain event when viewed from a different reference frame, which is moving at a speed which is comparable to the speed of light. I'm saying comparable, it should just be like any speed, but then we only use it when it's comparable, right? So yeah, it's used in those cases. It's not an approximation. You might be thinking that, okay, well, he said comparable, and for small speed it's not well. No, this should work all the time, right? So that's why I did all of this, so that I can clearly say this, and you can use this anytime, right? But usually we don't because it's just too complicated to use. There's a bit of a problem for length contraction that I faced. That was that events are not simultaneous, and then derivation just became too long for me to write down. So basically I only wrote down about time dilation, you can read this right now. It's not just a big thing. Yeah, so you can read this, and that will give you a good understanding of why this Doppler effect is in fact happening. Because we won't be dealing with x dash at all in our derivation, so just think about what t dash is, like how that's going on, right? Okay, so now you are ready for the derivation, I hope. And okay, I should actually explain what all stuff are. So you have x dash, that's the x coordinate of whatever event you are recording in the s dash reference frame. X and t are the x coordinate and the time coordinate, I'm saying, right? So those things for s reference frame, and of course for an event, right? So you are recording the same event in both reference frames. But then in S dash, you have X dash and T dash as the coordinates. And in S, you have X and T. And to get X dash and T dash from X and T, you can use these things. And V is, of course, the velocity along the X direction of O dash as seen by O, right? And you can use these for any events that you can like sharply record. Okay, so relativistic Doppler effect. So consider light as a bunch of photons going from O to O dash, and I've already given you the idea. So your photons are having space lambda between them, right? Any two consecutive photons will have lambda space, and then there's time period t, which is required to emit the next photon, right? Okay, and the photons are of course moving at the speed of light, c, right? So first of all, we are saying that a photon hits O dash at x1 t1 as seen by O, and event 2 is next photon hits O dash, which is at now x2 t2. I'm just declaring some variables. So first of all, we know what t2 minus t1 is because that's seen in the O reference frame. So whenever O will calculate the thing, I know I'm saying calculate, and you might be thinking like observers can't calculate, but we are in a reference frame. We are not saying that this is as seen by O. Okay, actually it is as seen by O because that's what this means. But do not get confused by frequency. Like, yeah, t2 minus t1 is not capital T. Capital T is the time elapsed between emission of two photons. This is not emission of two photons. This is the photons hitting O dash, right? It's different. So t2 minus t1 is equal to lambda upon c minus v. Why c minus v? Because your photons are moving with c and your O dash is moving with v. So relative velocity, the usual relative velocity, not relativistic, all right? Because we are still in our S reference frame. We are just calculating what's t2 minus t1, right? I mean, as you will record it from the S reference frame. That will just be lambda upon c minus v, right? So just understand that for now. We are only in the S reference frame. Okay, that's awesome. And also x2 minus x1, that will just be our v times t2 minus t1. Because in that time, you have O dash moving by v. So, right, I mean, wherever O dash is, though that is our x coordinate because that's where the photon has to hit, right? So now you got x2 minus x1 and t2 minus t1. Then you can use the Lorentz transform, so you can get t dash, which is t2 dash minus t1 dash. So t2 dash is the respective t dash when you put t equal to t2 and x equal to x2 in our Lorentz transform. So similarly, you will get t1 dash. Calculate those t2 dash minus t1 dash, call that t dash. That is basically the time elapsed between consecutive hits on O dash in the S dash reference frame, right? So using the Lorentz transform, this just becomes gamma times t2 minus t1 minus v upon c square times x2 minus x1. But then use the fact that x minus x1 is just v times t2 minus t1, and you can write it like this, and then substitute in t2 minus t1. So basically, you will just get this expression. So gamma times 1 minus v square upon c square times lambda upon c minus v. Now I just substitute gamma for 1 upon square root of 1 minus v square upon c square, and you will get this expression. Simplify a bit, you get this thing. And remember that lambda upon c, that's by definition capital T, because like, yeah. So that just means, because, yeah, okay, so lambda is, you know the thing. That much is very basic. So this is just capital T times square root of c plus v upon c minus v, and then reciprocate the whole equation. So just have 1 upon t dash, which is f dash, right? We are defining it like that. And then 1 upon t is f, and then this will get reciprocated as well. So just have f dash is equal to f times square root of c plus v upon c minus v. Oh, it should be actually negative of this thing because we just reciprocated. So this should really just be c minus v upon c plus v, but then you know the thing, right? So this is c minus v upon c plus v. And then this will be c plus v upon c minus v. So you got f dash, and lambda dash will be given by c upon f dash, because the speed of light is same in both reference frames, and it's having similar behavior, right? It is light in the end. So that's why lambda dash times f dash is c, and you can calculate lambda dash in that way. So lambda dash is just lambda times square root of c plus v upon c minus v. And there you go. You got relativistic Doppler effect for this particular case. There's also a lot of other cases where you have the observers moving in a circle. One observer is moving in some other direction other than the x direction, that is, right? They are rotating around each other, something like that, right? So if you want the formula for those cases, you should go to the Wikipedia page for this thing, right? They have those formulae, and this is it. So I'll end the video here. Okay, see you guys in the next video.